I think we're rolling. So good morning, everybody. Welcome to this very special lecture in a way, because if you didn't, so if you were reading this exercise last week, so you know what's going on. If you were in the exercise last week, oh, let me share this if I can. So I was half joking that there's papers for teaching NLP and teaching transformers and BERT, and one of them is by Ekaterina Artemova and her colleagues. And I remember this paper because they show this picture later on that to spice up the lecturer is dressed in an Elmo costume. So Elmo is one of the transfer models, like early ones. It's not BERT, it's a different one. And I found it funny, and I was joking. And then somebody said, like, I should be dressed also, like, to spice up the lectures. And I said, like, if you bring me the costume, I'm gonna do this. And you made it, so congratulations. It's your first lecture, like, so early, and I think also like the last lecture. That's okay. I mean, that's fine. So anyway, so this is the reason why I look silly, but I stand by my words. I shouldn't tell I'm gonna do this, otherwise, this is how it works. So let's do real things. So, oh, it's really warm in there, like on the head. So welcome to lecture. I feel really stupid right now. But anyways, let's do this like for real. So where did you end up last week in transformers? So we talked about BERT, the transformer model, and what is BERT doing? So I think this could be a good kind of model of a mental model of what BERT is doing. So BERT is taking basically an input which is some number of tokens, and one of the limitations of BERT and actually all transformer models is that we have a fixed number of inputs. So there is some k number of input tokens, and what we are doing is that for each token we learn a contextual representation. So sort of like embeddings, but in context of all the other words. And we talk about the internal mechanics of BERT. So that there's some layer, the input transformed into the input embeddings consisting of the token embeddings, position embeddings, and maybe something else. Then we talk about all these layers. So I think in BERT it was like 12 or 24 layers, and each layer consisting of several heads. And in these heads, there was this attention where we showed like, oh, each token is kind of attending to the other token to see what's important and what not. What's coming out of this is some sort of embeddings which we use for fine-tuning. We didn't touch at all, we just talked about the architecture of the model. So like, what are the functions in there, what is the attention and things like that. We didn't talk about how it's pre-trained, how it's used, although we use it in the exercise. Like we kind of used out-of-box pre-trained or fine-tuned BERT to use for some tasks. So, and what we are going to talk today about is how the BERT model is pre-trained, which means how do we start using this from scratch, basically, like how to get some good embeddings or good trained representations in there. How can you use it? How can we use it for different tasks? And why BERT is still useful in 2025, 26 as a model, and also a little bit going deeper into what is attention is actually doing. So are there some inherent properties of this attention, especially in BERT? So sort of like intrinsic motivation. Okay, good. Let's go for it. So what is the input for the BERT model? So do you remember? I mean, you should remember maybe word piece. What these are? So these are subword units. So what are subword units? Do you remember how word piece kind of worked? Or byte pair encoding or something like that? Yeah.
Like the very fundamental building blocks like letters and
Yes.
the punctuation, and then we just added the most frequent byte pairs
Yes.
to our vocabulary until we reached like 20,000.
Yes, exactly. So you start building the vocabulary not by taking tokens by white spaces, but you start with characters and merging basically iteratively the most frequent bigrams to create your vocabulary. So what is the advantage of this? Like, what is the advantage of having subword units as compared to words? What is the advantage of having subword units? Any idea? You have words and then you have subword units. What is, yeah?
automatically build your vocabulary out of tokens that are the most frequent, and especially for languages like German, where you have a lot of words consistent of multiple words.
Yeah, you have compounds, exactly. So what is the problem with compounds or like long words or some rare words? I mean, there's like fundamental problem which you're kind of bypassing with that. There is no out of vocabulary word. I mean, everything is in the vocabulary. You're not running into, oh, I don't know this word, OOV and whatever. So you have everything. In the worst case, you built every word from characters. Okay. So some models are like 30,000 of those, 100,000 of those. And the thing is, like, if you create your vocabulary or word, I call it vocabulary, but it's just like an inventory of subword units. If we build it from over multiple languages, you end up with multiple alphabets in there, and basically you make a multilingual model, which means there's all these, Latin alphabet. There could be Japanese, Chinese. Even though with Chinese, I think you'll be running out of, out of 100,000 characters. Sorry, 100,000 units. I think in original BERT there was Georgian as an alphabet. This is a very special alphabet, like only spoken in Georgia, and it's also in BERT. So I think, how do you do this? Like, what source would you take to learn subword units for all languages? What is the best source? Number one. Wikipedia, exactly. You take Wikipedia, run it through, and you learn all languages, all alphabets. Okay, questions? Makes sense, good. So what is the input representation? So we're talking about the word piece embedding. So basically it means each token from the token vocabulary, sort of, or inventory, has its own embedding. This is the same as word-to-vec embeddings. And these are initialized randomly. When we pre-train BERT, when we start from scratch, we say like a random embedding. So this is the same as we in word-to-vec. We start random. Then we talk about these positional embeddings, where we say, oh, for position 1, there is an embedding. For position 2, there is an embedding, and so on, to make sure that each input representation already knows where it is in the sentence. And, okay, input length is limited to, this is the original BERT, 512 word piece tokens using the padding. And there is also a few special tokens, so which will be very clear later on why they are important and why they are called as they are called. So the first token is always a special token called CLS. Any thoughts what CLS could be? It resembles a word that we use in like machine learning. Something like classification. Yes, it's abbreviation of classification. Why is it so? It will be clear later on. And if we have task that involves 2 sentences, so what is NLI? NLI, what is the task? NLI count. Yes? Natural language inference. So you have 2 sentences, text and hypothesis. Does it entailment, a contradiction, or neutral? So if you have such a task that you need to decide on 2 sentences, there are 2 sentences separated by a special token called separator. So you put a special token between these 2 sentences and you feed it in. And there's also, in BERT, there's something very special, and it's actually not that much efficient, but anyways, there's 2 segment position embeddings. So let me just show you an example to really see what these embeddings are doing. So here, here's the input. So the sentence would be, my dog is cute, he likes play ink, and blah, blah, blah. This is a made-up example, but it just shows that first we have here this subword unit. So the ing is, it would be like one word playing, but it's separated into 2 tokens because these are subword units. So this is one example to show. Then we're putting the CLS token as first, and we have 2 sentences. My dog is cute, he likes playing, and we put a separator in between. Okay, so this is the input, and then there's a separator at the end. Okay, so there's 2 separators basically separating like a dot, like a full stop at the end of each sentence. So obviously for each of these tokens, we have an embedding for CLS, embedding for my, and so on. So these are token embeddings. Then we have what we talk about already is the position embedding. So this is a position 0, position 1, and so on. So each position has its own embedding. What is also here in BERT, which is not actually used anymore, but they had it back in there, is sort of segment embedding. So there's just 2 embeddings, one vector for whether it's coming from a segment A, so from the first segment of this input, so my doc is skewed, corresponds to the first segment, and then there is a segment B, which is a single embedding corresponding to the second segment. It's just you want to distinguish whether it's coming from the first part or the second part. It turned out like these segment embeddings are not used anymore in transformers, but what it's still used is token embeddings and position embeddings. These are still used in GPT and all these other transformers. But I just wanted to make it very clear. Okay, any questions to the embeddings? What's coming in? Okay, so sanity check. What is the dimensionality of the, let's say, token embedding? So I have a token embedding. What's the size of the token embedding? Any idea? It turns a word into vector. So what is the size of the vector? Say again. No. Number of words in the sentence is the number of words in the sentence. It doesn't have to do anything with the size of the embedding. You take a word like a dog and want to turn it into an embedding vector. What's the size of the embedding vector? Yeah, we can arbitrarily choose it, exactly. So it could be something like, I don't know, let's say a number 300 is as good as any other. 1,000 something maybe, depending on how big you can go with the model. So everything kind of, if you have a big, input embeddings, you might end up having just a few layers, or you want to have more layers and fewer size. Basically, depending on the size of the model, it determines the number of overall parameters of the model. Okay, so let's talk about pre-training. So how do we train this model? So why is it pre-training interesting? So remember, word embeddings, static word embeddings, were trained just by using plain text. And then we use them for some downstream task, like we plug them into, oh Jesus, it's getting really, really hot in this. Yeah, I don't want to disturb the thing. No, I'm gonna suffer, it's okay. I'm just saying like, so we use these static word embeddings and pre-train them on just some text, and we learn the static word embeddings. So, and then we use them later on as a transfer learning, sort of. This is the paradigm. So we pre-train on something which is very cheap and we have plenty of data about, and then we use these representations to do them, to use them for something else. So how do we pre-train BERT? This is actually very interesting. So it's called self-supervised because we don't provide any labeled data. So we don't give the pre-training data. There's no human sort of annotations. We just take some data. It's called multitask. We talked about multitask learning last lecture, right? You have, one common architecture, and there is multiple tasks coming out of the model. We talk about, I don't know, something part of speech tech, whatever. So it's multitask because we're gonna pre-train it on two tasks at the same time, or we're gonna, switch between those. And it's called pre-training because it doesn't solve the task we want BERT to solve. It doesn't solve classification. It doesn't solve anything. It's just how to learn the best parameters, sort of, or the best weights for the embeddings, the best weights for the projection matrices, the best weights for the attention matrices, Q, query, key value, all the parameters, such that it will be helpful down the road. Okay, so there's two tasks which we're going to use, and there's no need for labeled data. We come to that in the next slide. So the task one is sort of closed test task, which is we take a word. Let's say randomly pick this word, which was, I don't know, some word. What was the sentence? My dog is cute, he likes playing. So maybe we take randomly the word he, and we sort of mask this word. And what we want to do is that from these embeddings, we want to predict the missing word. It's like fill the gap. It's sort of like language modeling, because in language modeling, you have a sequence of words and you want to sort of predict the next word. Here, this is a sequence of words, left and right, and you want to predict the middle word. It's also similar to word2vec, where you have words on the left, words on the right, and you try to predict the target word in the middle. So basically, we're trying to learn such a representation of all the context that it can kind of infer what's the missing word. And of course, if you have if you're as a human, you have a sequence of words. I don't like a text on Wikipedia. and you delete a couple of words, some of them you will be able to fill in with some linguistic properties, with, I don't know, what you need to fill in the words, like knowing something about a topic, like the world knowledge. You need to know something about grammar, the language, maybe some will be some linguistic structure and things like that. So this is the task, like we want to model to train to fill the word. Questions? Okay, cool. The second one is also interesting. It's we want to predict whether the second text appeared after the first segment. So what we are going to do, we take these two sequences. My dog is cute and he likes playing, and sometimes we leave them as they are. So sequence 1, sequence 2. But sometimes we can do what? We can shuffle them randomly. We just say, oh, you know what? Just flip this and start with he likes playing and my dog is cute. Or we can just take I think that's what they're doing, like shuffling the order of these two sentences. So basically destroying sort of the coherence of the text. Because if you have like a long sentence at the beginning talking about something and then it continues to talk about the same thing afterwards, the model should know, oh, there's some coherence between these two texts, there's some dependencies. If you flip them, it shouldn't make sense. And that's what you want to also, the model kind of be sensitive to. And we're going to train the other task, which is a binary task, like, oh, did sentence 1 appear before sentence 2 in the original data, yes or no? That makes sense? Okay, very good. So these are the two tasks, which is, well, it turned out later on that this consecutive segment prediction is actually not super important. I mean, it was important back then, but you know, if you have more data, bigger models, you don't need the second task. But the real task, which really matters, is just fill in the word. Like try to guess what the word is in the middle here. Okay, so far so good. So where do we get data for training this BERT model in multiple languages? Exactly, Wikipedia again. Yes, sure, absolutely. You know why?
The data. So if you take, say, I don't know, if forum or something like this, it would be sometimes garbage.
So exactly. So you're talking about quality. So if you take a Reddit, it's gonna be really bad, like in terms of quality. You're right. So I mean, also nobody cares about these things anymore. But back in the day, some people actually cared about the license of the data. So you can take Wikipedia; it's open source. Like it has a permissive license. You can do whatever you want. These days, ask Meta. You know where do they get their data for training Llama or OpenAI and stuff like that. Yeah. So Wikipedia is free. And there's also the multilingual. It is, as you notice, like if you have multiple languages, you can train over multiple languages. So they took the entire Wikipedia, like in 100 languages, 2.5 billion words. It's actually small from today's perspective, but it's better than nothing. And so you take the entire Wikipedia, and to generate a single training instance, we first take a page of Wikipedia and sample 2 segments. So we combine, these segments coming in, so these segments, here it looks like a beautiful sentence, but in reality, this is just a random subset of 500, something like half of 500, like 200 something tokens from the second part of the page of Wikipedia, and then the second will be like, afterwards, the second segment of the page on Wikipedia, some randomly. So these won't be sentences, it's just a segment of text, like 250 tokens, whatever that is. So you take that, and for the second task, like what's coming first, oh, actually no, they didn't flip it. They replaced the second segment randomly in half of the cases. So they basically, so you first take first part of the Wikipedia page, you flip a coin, and if it comes heads, you say, oh, I'm gonna take the second part as a second segment. If it comes tails, you say, oh, I'm gonna take a completely different Wikipedia page and sample the text from there and put it like afterwards. So then the task will be actually not what comes first, but does it even make sense? Like this is the first sentence or the first segment and the second segment relevant in any way? And the idea is like if it's coming from completely different page, it will be completely irrelevant. And the model should kind of try to predict this. while at the same time learning the task 1, which is choose some 15 number of tokens, and in 80%, why? Or whatever. So you take some random, why is it 15 and 80%? Anyways, you take some number of tokens and just put in a mask token. So this is like you try to replace the input, not to try, you replace the input with this mask word, and the idea will be if you put mask here, that you need to try to predict the missing word, like what you put in there instead of mask. Any questions? All right. Yes, you have. Yes, sometimes. Yeah. So if you take 15% of the tokens and in 80%, so what is 0.15 times 0.8? I don't know.
15% of the sentence, and then we decide if we mask it or not.
Yeah, something like that. Yes. Well, I mean, you could basically do like what is this 0.12-ish something. So 12% of tokens will be replaced.
Oh, okay.
Something like that. I don't know why they do like this. Maybe there's a reason why it's like first selecting the tokens and then masking. But basically, you just take a random sample of tokens and mask them, like 10% of those. And this is actually what is the most efficient method of training these weights of the model, the masking. And if you think about it, yeah, it makes sense. It has to predict the missing piece of information, and whatever the information is, it could be all these like linguistic, word knowledge, and things like that. So here's an example of a very simplified, so pre-training example. So we have the input, which is the special token CLS. The man went to, then we mask the word store, and there's a separator. He bought a gallon something of milk and separator. So what could be what's the mask word here? The man went to okay. Any other options? Yeah. A, yeah. Any other? I think this is the only thing that makes sense, sort of. He bought a gallon of milk. I think there's no other choice to be here. And this is a very simplified example, of course. So, what we're missing here, what we're putting here is the articles or some other part of speech words. And as you might see, I mean, this whole sentence makes sense, so which means like the label is next is true. So the second sentence is coming after the first one. Okay. Yeah. And for the other one, the man went to the stars again, and penguin mask. What is here? Penguin are flightless birds. What could be the mask? Penguin are flightless birds. Penguin species, maybe? Any idea? Other idea? Oh, maybe it's penguins. Penguins. Yeah, that makes it like penguins are flightless birds, which is not next. Okay, cool. I don't know the true answer. I mean, I took it from the paper actually. So, okay, so this is how we prepare the input, and then how do we pre-train this by mass language modeling? So we prepared for a very ugly slide, which is this. And yes, it's a very ugly slide. But now, actually, you know what? It actually makes sense. I mean, if we just go through this, you will see a familiar pattern. So what we are doing is that, we're okay, whatever that is, function, blah blah blah, parameters, masking. I don't know. Let's see later. So we iterating over a number of epochs. Okay, I mean, we know number of epochs in standard training. We basically run through the data. And if you run through all the data, training data, we go once again, and this is called epoch. So basically, one pass over all the training data is called an epoch. So we run for the epoch. Okay, then we're iterating over the data. Sounds good to me. We take an example at a time. So far, so good. And then so this is the xn will be the training example at the moment. So we have a training example, which is this, 2 sentences, 2 segments. And then we're gonna do this, what is this, tilde x at position t. Well, basically we're masking token at position t with some probability, otherwise we keep it. So this is basically the masked the masked input where we, let me see, where we just decided on each word, whether we're gonna mask it like here, or we're just gonna keep it. So now this x tilde is the mask word. And we also keep the indices of the mask words, which means this is sort of set of all these indices we were masking before. I have an example in the next slide. So of course, if you remove words, you wanna remember somehow, you know, which words you removed, because you wanna try to predict them back. So far, so good? Okay. Then there is, we run it through the transformer. So we put it to the function we described basically last lecture. The input of the transformer, all this fast, you know, feed for, for this like the forward computations, and we get a distribution over vocabulary. So this is the output that we want for each of the output embeddings. So for each word, we want a distribution over vocabulary. Why do we want a distribution over vocabulary? Because we're trying to predict the missing words. So it should try, at the position where we are, it should try to predict the missing word. Then, what we are doing here is compute the loss, and then, I mean, the loss is something which we're gonna decipher next time. But we wanna know how bad the model how badly the model was able to reconstruct the missing word or not. Like this is just a standard, some sort of loss. I think what we're gonna use is some sort of cross entropy. So there is a cross entropy loss, and then this should be familiar to you. So we take the learning rate. This is the gradient of the loss, and we update the parameters. How is this algorithm called? You know this algorithm already. It's the only algorithm we actually talked about. Yeah. Backpropagation will give you this. There will be backpropagation to compute the loss, but the whole thing. This is just gradient descent. This is just gradient descent. That's that, and this is not even stochastic gradient descent because you're not sampling these sentences randomly. You just take one after each other. So we take a sample, compute the output, get the loss, update the parameters, and continue. And of course, you can batch it if you want, like doing like stochastic, mini-batch stochastic gradient descent. But this is just the stochastic gradient descent. That's what I saw. Like it looks horrible, but at the end of the day, it's an algorithm we know already. So we train BERT with stochastic gradient descent, nothing else. Yes. Eight.
Yeah. So I thought we would get, after the transformer, we would just get a representation of the sentence.
Yes.
And not already.
So this is a good point, because last lecture I talked about like how to use the output of BERT. Let me just scroll back a little bit to show this. Maybe I have it here and maybe not. So here, typically, we have these embeddings for each word. This is what's coming out. It's for each word, we have the contextualized embeddings. This is what you want to do for your task down the road.
Right?
Yes. But also, what is the output of a transformer depending on how you call it? Because we can also take this and each of them turn into probability distribution over the vocabulary or the word pieces, which will be like size of the vocabulary and probabilities. I mean, we can basically softmax or project and softmax each of these vectors into probability distribution over the vocabulary. And there will be some. This is just a linear projection of this embeddings to some smaller to the size of which is like 100K. So we project this 300 tokens, 300 embeddings into 100,000 sort of vector. So there's just one linear projection. We run softmax on that, and we get a probability distribution over tokens in the vocabulary. Does that make sense? Okay. So this is only useful for the pre-training. We don't use it for the actual like downstream. So this is just for pre-training. Is turning this into the P here. Excuse me. Let me come just back. So this is sort of a matrix. So for each row in this matrix, this is a probability distribution over vocabulary. Each row, exactly. Yeah. Each row, like each token, because we want to try to project. Every of those goes to probability distribution over vocabulary, so histogram. This one as well. Why is it so? Because if you mask a token, let's say this one, you want to try to predict the missing word. Like this should give you like, oh, actually, if I turn this into, I mean, my histograms are horrible. I hope you understand this is a histogram, okay? So you want to say, oh, the word which is missing was the maximum value, which was this position, which corresponds to the word dog, for example. This is how you want to try to reconstruct the missing word. Okay? Good. So let me come back, because we're gonna dissect this algorithm more in detail on an example, just that we understand it very well. So this is how would you basically try to implement this. Okay, so the masking on line 6 and 7 is kind of it should be self-explaining now, because there's nothing should be nothing surprising in there, but let's just go through this. So we have a sentence, the cat said. We turn it into indices in our inventory V. So this is like 100,000 different subword units, and the corresponds to position 21, cat corresponds to this position, and set corresponds to the other position. Okay, so we just do a lookup in the vocabulary, like what is the position of this word. Good? So far so good? Okay, cool. Then random masking. So we have this very special token, which is called mask token. Okay, so the V size of the V is 50K. And at position 50,001, we add this very special token called mask token. So the index of the mask token will be 50,001. It's an arbitrary decision. It just had, every token has to have an index. And we go through all these tokens. So the first is the, for position 1. The random outcome is that we should mask this word. Okay, so we're replacing the first word, 21, with the mask word 50,001. Then we go for the second word, the random outcome. I mean, we're flipping sort of this like with probability 10% or 12%. We're keeping the word or we're masking the word. So the random outcome was keep, so we keep this word. So basically, we just copy the index here. And then for a third token, the random outcome is we should mask this. So again, we turn this into the mask word 50,001. It's basically replacing random words with the index of this mask word, basically. Okay, everybody's fine with that? Cool. And what is this? I mean, we keep indices of words which we mask. So we mask word at position T1 and we mask word at position T3, because this will be important not to forget. Like we need to reconstruct these words. We need to reconstruct 21 and we need to reconstruct 500438 later on, these indices. Okay, so this was the algorithm at line 6 and 7. Like basically these two things now are actually very clear what we're doing here. We're just masking the words and keeping the T, tilde T. Okay, now we should explain this line, like what is this? I mean, it looks like a cross, it should be something like cross entropy, but why is this just this weird indexing and logarithm and minus? I mean, it looks like cross entropy, and it is actually cross entropy. So let's say we run these 3 tokens through the transformer. So why there are 3 lines here? Why do we have, so this is the output of the transformer. So we run this input, we run it through a transformer and get this matrix. So just a sanity check. So what is this size corresponding to? Exactly, 3 input words. Okay, what is this line, this dimension corresponding to? Yes? Excuse me? The first word, I mean, this is the number. So what is the number of columns here? What is it corresponding to? Yes? This is the size of the vocabulary, exactly. Because we're projecting now, this is what we're talking about here, is that we're projecting each token representation back to the vocabulary. And this is how we get a matrix. I mean, this is, I made it here separately for each row, but it's actually sort of a matrix, like a bunch of vectors after each other. So for each token, we have now a probability distribution over a vocabulary, and the size, of course, is the size of the vocabulary. Okay, so here, yeah, actually, yeah, exactly. It's each row of P is a distribution over the vocabulary. Good. Questions? So far, so good. Okay, so this is the output of the transformer. And now, we have to explain the negative log likelihood. Okay, so let's just go step by step. Because let's start at position 1. So at position T1, so this is the first token. The input was 21 something something, so this is the cat set. And after masking, we have this mask token, kept the second word, and masking, and these two were masked. So now we're taking the first position, so this is T1, so the first row basically. And for T1, the model should learn to predict what? To predict the index 21. So basically, the model should kind of try to reconstruct itself now, try to reconstruct what should be the word we are trying to learn. What is the word which was in the input? So basically, it's trying to learn itself. Like the word was in the input, and it tries to predict the same word. But after going through all the transformer thing, like there is all this context from the other word. So it's basically learning the best representation, how to best represent the word in the given context. And what is the gold standard for this? Oh, the gold standard, like we need to, if you do like any sort of loss, you need to compare the output of the network with some gold standard label. And the gold standard label for this example is basically one-hot encoding, which means at position 21, which corresponds to the index of cat, there is 1 and everything else is 0. Does it make sense? One-hot encoding of cat is this vector. Position 21 corresponds to the index. Okay, so far, this is the gold standard. The prediction is basically this vector. So this first row in the matrix corresponds to this vector, and they have the same dimensionality. Like this is what's coming out of the network, and this is what the gold standard should be. So we have two vectors. We can run like cross entropy on these two, because these two are just basically distributions. So if you know categorical cross entropy, then you know how to compare these two distributions, so to say, to get your score. Like how far are we with this prediction from predicting this? So this is the definition of categorical cross entropy, if you recall. And yeah, let's have a look. So it simplifies actually pretty easily, because you can actually, here in the gold standard label sort of, everything is 0 except for the 1 at position 21. Which means we can just completely ignore all these, 50,000 summations, 50,000 summands. We just pick this and this, because the rest will be 0 anyway. So this is where we pick the prediction of the network at position 21, right here. This is the interesting number. And we multiply it by 1, of course. And we turn logarithm. We have the minus here, so we keep the minus here. Okay. So this is what we have. Oh, it actually simplifies to, we just get rid of the minus. It simplifies to, now the notation only, it simplifies to taking the all matrix at row 1, so this is the first row at position 21, and taking a logarithm. And if you basically, this is it. This is the final computation, and we can turn it into this generic formula that we take a minus logarithm of the entire matrix coming out of BERT at position t and at the input for the position t. So this explains basically why. This basically explains the formula, but it's nothing else than just a cross entropy. Like you have the one-hot encoding of the gold standard, sort of like the missing word, the index of the missing word, and you take the probability predicted for this word and take a logarithm of that. Like basically you take just the negative logarithm of the probability predicted for this word. It simplifies to one simple operation, just in lookup here in this matrix and taking the negative log. And this is just how it's represented here for just ease of indexing. It's very hard to read kind of, but it's actually very easy to implement. Okay, questions? If it doesn't make sense, just go through this example, because I had here the same here for the token at position 3, for example, which is also masked. I mean, yeah, we do this we do this only for the masked words, of course. We take only the mask, we try to predict the masked words. I made a mistake. We're not trying to predict all the words. It wouldn't make any sense, of course. Yes, apologize. We take just the masked words. So here for position 3, again, we take, so the position 3 was this missing index. It was the set. So we take the prediction at position 5000 something, so just the missing index, take a negative log, and this gives us something. And then we sum, so for each of the mask tokens, gives us a cross entropy for each token, and the overall loss is just going to be a sum of those. Because we're summing, so we have a network, so let's say this is a token 1, token 3, and there is a loss, and there is a loss. But we are minimizing the overall loss of the network, so we just sum them up to get the total loss. Like you make a mistake for token 1, okay, got it. You make a mistake for token 3, okay, good. Let's sum up them together to get a final loss, because a loss function, if you recall, loss function is something just giving a real number. So it has to be a real number and it has to be positive. And you want to make the loss as small as possible. So you want to make a loss small at position of token 1, you want to make a loss small at position token 3, so you just sum them up. That makes sense? Okay, very good. Questions? Can you repeat just? Sorry,
So
I didn't hear because I.
the model doesn't know what exactly it did wrong, so which word did it predict wrong, but it just knows how wrong it actually is.
So you're asking the model didn't know which word was wrong, but it knows how is it wrong? In a way, yes. I mean, the overall loss doesn't care where the error was made. So this last function is summing the last sum here, the loss, is just saying what's the total loss of the entire model. And you're gonna say, okay, so I have the total loss. Now I have to, now I have to compute, and I have to do the gradient. How do you compute the gradient of this network? Oh, so you start with the loss, which is a sum. Then you have to say, oh, how do I propagate this error to all the nodes? So you'd say, oh, what is the partial derivative of this loss with respect to the first token loss and the third token loss, which is very easy. What is the partial derivative of sum? Very, very easy. I mean, it's a very easy partial derivative. So you start, oh, okay, now I know what is the loss for this token, I know what is the loss for this token, and you start by propagating through all the network. So basically, yes?
Is there a punishment for mask words that are very, let's say, easy to predict for the model? For example, there's only one possibility. Let's say example before.
Oh, so you're asking whether there's more punishment. I mean, so there's no difference, like no a priori differentiation between words. Like you don't tell the model, okay, this word is easy, this word is hard, nothing at all. So it might be that if this is an easy word, the model will learn it very quickly and then will make no mistakes later on, which means there will be like very small loss, because if you go, I mean here the closer you come to 1, the smaller the loss will be, which means the word was easy to learn. So if this is an easy word, like after a few iterations, the model should be able to kind of predict it well. And there will be words which are ambiguous, and the model is actually uncertain which word should be missing in there, which sort of makes sense. Does it answer your question in a way? Okay. Other questions? Okay, good. I mean, so now we know how to pre-train BERT. This is nice. Yes?
I have a feeling that I don't see the model learns the context here. I have a feeling that that model just learns word by word.
Yeah, no, exactly. But yeah, the how does the model learn the context in here? Because here, what is it doing? So just a very high level summary. I don't have the slides from last lecture. I mean, I can open up the slides from last lecture, but it takes embedding for each word, but then it's combining them through this attention. So you make which words attending to which word, and then you're adding the attention, you're weighting the other tokens, adding them by the attention, and outputting the whole sum of that. If you look at the attention head, there is this clear path from left to right, I mean, for you from left to right, and then you go through the attention head, where you learn these kind of inter-word dependencies, and you add it back to the matrix. Then you go through feed forward, add it back to the matrix. So through these paths, attention and feed forward, you encoding the entire context of the sentence into the embedding. So at the end of the day, sure, I mean, you have just for each word, you have a single embedding. But in this embedding, it has seen through all these 12 layers and each layer 24 heads, whatever, it has seen all the context and it encoded the context in the embedding. Does it answer your question? Okay, cool. We have an example of these, of what is attention actually doing at the end. So then maybe we'll, it will give you some intuition as well. So far, so good. So pre-training, let me just come here. Okay, so now we have a pre-trained BERT. And let's say, well, pre-trained BERT can do only two things. It can tell you which word is missing, and it can tell you was it one after each other. So it's completely useless for anything like any NLP task. But it's a pre-trained model, and we can try to sort of fine-tune it, which means we take the existing weights, we take the architecture, we take the pre-trained weights, and now we can start training it for some tasks. And this is going to be interesting because remember the CLS label we had before. So this is a, because each token and ending up with a embedding, even like these very special tokens like SEP, it's going to be its own embedding. But of course, these words also has embeddings. So now we have a sentence pair classification task, such as natural language inference, and some others, whatever, textual entitlement things. So you have sentence 1 and sentence 2, and you want to predict whether there's an entitlement, contradiction, or they're neutral, like some sort of classification task into 3 categories. So what you can do is, if you put this, these 2 sentences in this format like CLS, all the tokens, separator, all the tokens, and separator into BERT. And then what's coming out of here is, all these tokens, but also the embeddings for all tokens, and also the embedding for the CLS token. And of course, in this embedding, there is all the sequence encoded somehow. So it encodes the entire sequence because everything here is connected to each other. So there is the whole sequence attended. So you have an embedding for your entire sequence. You have one embedding for the entire sentence. And what you're going to do with that, you project it into, let's say, three-dimensional space, run softmax out of it, and you get a classifier. So you basically classifying you learn a good representation of the entire sequence, basically of 2 sentences. You learned basically the representation of these two sentences after each other. And you can put a sort of like multi-layer perceptron, or like just one layer on top of this CLS token to run predictions. And you can turn this into classifier. It could be binary classifier, it could be a 3-way classifier, whatever. I mean, it's just you plug it in as into the network at some tiny little like, oh, let's project to 3 dimensions, then run softmax. And then you would have a loss, and here you would have a gold label, which is a vector of 3 categories. Just a standard network. And you can train this thing, you have, for example, natural language inference, you would say, okay, so for sentence 1, sentence 2, like, what is an example of NLI? Kids are playing football outside. There are some people doing sports, which is an entitlement. So I put it here, the first sentence, second sentence. The gold label would be, maybe entitlement would be 1, 0, 0. So I'm running this through BERT, take this embedding, project to 3 dimensions, run softmax, which will give me some probability distribution. I compute a loss and train back the model with the propagation. I can train the whole model if I want on the task. Okay, does it make sense now? I mean, this is just a bunch of parameters in the model. I can run backprop and train all the weights, like all the million weights if I really want. And I'm fine-tuning the model. So the model has some pre-trained weights already everywhere. But for this special task, I'm just running it through my label data, and I'm projecting back everything and trying to update the weight such that it works for the task. And it has a strong advantage because the model already understands language in a way, like lots of things. I mean, we pre-train it on the whole Wikipedia, so it knows a lot of stuff, knows whatever it means. It's encoded in the model. So if I try to fine tune it on a task, I'm not starting like from complete scratch. I'm not starting from random embeddings. I'm starting with something where all these embeddings, all the projection matrices already know something about language, which is very powerful. So questions to fine tuning on classification? Sounds good. Okay. So, well, I mean, here I can represent, I don't know, 1, 2, 3, 4, 5, 6, 7 tasks. Good. Can I do more? Well, yes, actually, yes. I can take just a single sentence task. So I put it like first starting with a CLS token, then put a sequence here, and then at the separator at the end, I have just one sentence. That's fine. It won't break anything, basically. You know, the model should know how to work with this. And I can do like single sentence classification task like sentiment analysis or something else, like IMDb. Imagine IMDb classification. You put a movie review here, and again, what's coming out of here is a class label. I do like projection to a real number, put it through sigmoid. I would have a loss here. Here I would have the gold label, which is either 0 or 1. And I train the task. Okay, like, oh, is it a positive review? This should be 1. I run the sentence through a BERT, take this output. I basically ignore all these other embeddings. I can ignore them. I don't use them for this task. I just take the output of this, put a little small layer on top of that, just project to one real number, go it through sigmoid, just to get like probability sort of between 0 and 1, and the loss should be some sort of cross entropy loss. And I can train the model as well to do like binary task. Sounds good? It's actually very cool, isn't it? Like we solve the 2 tasks at once. Like we have 2 sentences after each other. We have 1 sentence classification, but we can do more. And this is actually very cool now, because we also have, for each of these tokens, we do have the embeddings, of course. We have, you know, for each token, we have embeddings, which are a very good representation. So we can do NER, like named entity recognition. We can do any other sequence labeling tasks. We can do, I don't know, part of speech tagging, noun, verb, and things like that. So we can basically run on each of those. We would add a sort of layer, classification layer, and then we can do. It's actually very similar to what we had in recurrent neural networks in RNNs, where we, for each input, we would basically try to predict the output. So each token, oh, is it a noun, verb, or something like that? And we would predict the output, and take the next token and predict the output. It's the same thing. Now we have representation, contextual representation for each token in the sequence, and we can just predict something out of this. Does that make sense? Very cool. So it's one model doing like very many different tasks, which are classification tasks. So the model doesn't generate language. Like, this is very important to remember. We don't use this. This is encoder model. It learns a good representation of the input through this transformer, through this encoder. It's very good for classification, but it's not intended for text generation. I mean, it could theoretically, you can hack it somehow to. No, like you don't want to do this. There's a little bit different architectures for doing text generation. This is just for classification. It has been very very useful. Okay, questions? So we are playing around with BERT using already pre-trained BERT. For the exercise today, there is basically how to do this fine-tuning for different tasks. So how do we fine-tune BERT for, what was that? Like some sort of document classification and things like that. So have a look at the exercises, and this is something you should really try on your own. There's a recipe how to do this in Torch and Hugging Face transformers. And basically, you will learn how to fine-tune your BERT model for the task of your choice. If you fine-tune it, your result, your accuracy on your task will go up. Okay. So let's talk about how much intensive was back in the days, 2018 was BERT. Was pre-training BERT at the time. So it took them 4 days on 64 TPU. So this is like something like GPU, but proprietary by Google. Tensor processing unit, whatever. So it took 4 days on 64 TPUs, and everyone's like, wow, okay, so how do you get like 64 TPUs, GPUs, it's really like, it was considered huge. like world has changed quite a lot. So 64 TPUs for 4 days, like very expensive. I think like $1 million or something like that. Like it was really, really expensive to train it. Once you pre-train this, then the fine-tuning actually is not intensive at all. I mean, you can use like, a GPU to fine-tune your model. I mean, these days you can actually pre-train BERT on your graphic card at home if you really try hard. Like if you have something bigger than 16 gigs in 3 days, I mean, it will cost you some electricity, of course, because I mean, like if you have 400 watts and it will be like crunching the numbers, 3 days in a row, it will cost you like, I don't know, 10 euros, something like that. I mean, it's true. I mean, you have to think about this. Like, running like GPU full time, it takes electricity. But it's, compared to 64 TPUs back in the days, you can do this. I mean, there is a blog post on the internet like how to actually implement BERT and train it on custom hardware these days. I think you need something bigger than 16 gigs. I mean, if you take 16 gigs, you can train on the small model because, I mean, of course, I didn't mention this, but there are several variants of BERT. One is BERT small, BERT big, and they differ in the number of parameters. What it means, differing in number of parameters, they differ in the number of layers. Like, is it 12 layers? Is it 24 layers? How many attention heads? Which basically everything corresponds to a number of parameters. So how big basically you double the number of layers, your parameters just scale by factor of 2, for example. So you can train a small model at home if you want. Like these bigger models, you would maybe need like bigger GPU, like something like, I don't know, NVIDIA A80, maybe 80 gigs, 800 like with 80 gigs should be good to go. A couple of days but still, it's very, very intensive. And this is a very small model, if you compare this to something like GPT, you don't want to know. Okay, so this is like how BERT works internally, and now let's turn into like how can we use it for something useful, even in these days. Although like BERT hasn't, I mean, it was an excellent achievement for NLP, but then later on a little bit different architecture took over all these GPT-1, GPT-2, 3, and so on, and the rest is history, sort of. But even in these days, BERT is really interesting for some usages, and one is through SentenceBERT. So SentenceBERT, the idea is that we had this CLS token, which kind of knows the entire input. So it's basically learn a vector for the entire input sequence. What could it be used for? So, I mean, it gives you some vector representation, and the idea is like a similar in Word2Vec, similar tokens should have similar embeddings, right? Here, the idea, like similar sentences, should have similar embeddings. What is it good for? Well, it gives you a way to compare whatever it means, or to measure sort of a distance or similarity of two documents. How do you measure that two documents are similar to or two sentences are similar to each other? You can run this as a document 1 and document 2 and run it through and then do some projection here saying, giving you some number, like how similar are they? But this is very expensive, like running through all these kind of bloody things, all these computations. Well, maybe there's an easier way. Maybe you just need to, maybe we just need to project it into a vector, and then you can compare two vectors of two documents to get some sort of similarity. What this could be good for? Like, how about search or clustering? You have a bunch of documents. Like, imagine you're a company. You have like 10,000 of documents, and you have no clue what's in there, and you want to cluster these documents, which means they are somehow similar. And then you can look into the cluster and take an example and say, oh yeah, maybe this cluster is about finance department. Oh, this cluster is about like strategy for research and stuff like that. So you can cluster based on similarity, or you can measure distance between two documents. And this was the motivation for SentenceBERT. So it's basically state-of-the-art performance on sentence per task. So semantic, textual similarity, or similar. And they tried this, so this is by Niels Reimers and Irina Gurevich, my ex-colleagues in Darmstadt. So they did this in 2019, and it's now, I think these days, SentenceBERT is used like It has like millions of downloads on GitHub, and it's used in companies for doing semantic similarity search and stuff like that. Like there's something called like vector databases, if you heard this, where you encode a document into vector, and you can do like fast search in your database. Some of them might be actually using SentenceBERT or some sort of similar approaches. So you encode your entire document into vector, and then you can search or cluster them or whatever. So they tried with BERT initially, and like finding the most similar pair. So you want to find two similar documents in a collection of 10,000 documents, and just using plain vanilla BERT, it would use like 50 million inference computations and 65 hours. I mean, imagine if you have a collection of 10,000 documents, it takes you 65 hours to find two very similar documents in a database. I don't think it scales, like not really. So BERT is really not good. Like vanilla BERT wasn't suitable for semantic similarity search or like clustering. So they needed to map each sentence to a vector space, and the idea would be that semantically similar sentences are close to each other. So this is like the intention behind word2vec, and now it's the intention behind SentenceBERT. You have two documents which are similar to each other in this embedding space. And what they did is, you can take, for each token, you can take the output layer for each of the embeddings. Like for each token, take the embeddings and take the average. This would be like sort of representation of your sentence. Or you can take the CLS token, but it didn't really work. So this is not the best representation for this semantic similarity thing. So what Niels did is, you take two BERT models and sort of connect them via shared parameters. So you take first sentence as the input, and you pull it into one BERT model. And you take another sentence, which you're trying to predict to be similar or not, and put it into another BERT model. But these two BERT models, they have shared parameters. What does it mean, shared parameters? Well, what are parameters? It's a matrix, all the matrices for all the weights, basically. The embeddings, position embeddings, token embeddings, then all the weights for each layer, each attention head, query, key, and value have matrices for projection. So all the matrices for projecting, all the weights for projecting the key, query, and value for each head, for each layers, these are the parameters of the BERT, and maybe all these parameters for the multi-layer perceptron and stuff like that. But these are just matrices. So you can say, oh, this model is using, you just basically say, oh, by the way, this is my bunch of matrices, like a vocabulary of parameters. And let initialize this model with these parameters and initialize this model with these parameters. So they are shared, basically. So we have one model referring to these parameters, the other model referring to these parameters, and they're shared, and you just run this whole thing. It's basically a computational graph again, but the weights are shared together. It's a still computational graph. It's still direct acyclic graph, but not each model has not their own parameters, but the shared one. So you run this sentence through BERT, and pooling means you find from a bunch of tokens. Pooling means you have for each token you have a vector, and you try to pick just a single vector for the entire sentence. So you can take, for example, the maximum for each item in these vectors. You can take the average. You can somehow clamp this together. So the idea is like you somehow, from this matrix for each token times dimensions, you clamp it into one vector by pooling. I don't know what it is exactly, but something like max pooling or things like that. So you get basically two vectors. Oh, interesting. And then this should be your great representation, your representation of your vector of sentence A and vector of sentence B. And here what they did was pre-training, basically deciding whether, I don't know, like some supervision from SNLI and multi-NLI. This is about the training. But basically, let's ignore the training for now. It's not super important. The idea is that once you train this shared parameter, the shared model, you get much better vector representation for two sentences for similarity. And I took it from research paper. In every research paper, there has to be a very huge table with numbers, and the bold numbers are the best ones. And if it's yours, congratulations. If it's not yours, then you have to say like, whoa, why is my paper actually interesting in the first place? So this wasn't the case. So the SBERT was actually giving all the best numbers for these different tasks, whatever they mean, some sort of similarity tasks. And there's some evaluation of that and basically saying, yeah, we have much better representation than all the other kind of representations. But the thing is about the thing about SBERT is efficiency. So again, we had this clustering of 10,000 sentences with 65 hours. With SBERT, we were able to reduce the effort about to 5 seconds. Okay, so going from 65 hours to 5 seconds, it's a game changer. It's usable now. You can actually use this. With 65 hours, you cannot use it at all. So it's like you get state-of-the-art results, and it's actually very efficient. So that's why SentenceBERT was picked up by very many, like, oh, I need representation of a sentence as a vector. What do I need to do? Oh, SentenceBERT. Just in the first kind of like baseline solution. And it's actually very nice documented. You can download it, play around with that, try to do some similarity of sentences, very nice API, very nice model, very efficient. Still updated. Niels has been working on this since then. So I highly recommend to. If you're interested of a tool for sentence representation, go to SentenceBERT. Okay, so this is one of use cases, and now we discussed last. Any questions, SentenceBERT, or yes? Yeah.
So if we would compare two sentences, we would take the same model and look at what.
Yeah. The idea is that they will have a different input. So you can of course take one big model and concatenate these two sentences. You could take sentence 1 and sentence 2 and concatenate here. That's possible, but the problem is also the context of BERT. So you want to have it as long as possible. So you take two models. Each of them will end up, because you want to learn so this is just for training. Excuse me. Let me just come here. This is just for the training, but eventually you always have just one sentence. So you want to have a sentence, this BERT model, and this during the inference time. You just plug in a sentence and it gives you a vector. So the model should be ready for just accepting one sentence, not two sentences, just one sentence, and give you the vector.
I understood that.
Yeah.
But I thought we would just take one BERT model, we put in the one sentence, we get an output, and then we take the same rule and then we put in the other sentence. So why should we take two different BERT models?
Oh, okay. Of course. So this is the idea. Yeah, sure. At the end of the day, what you're saying is that these two models are not different because they have shared parameters.
It's basically the same model.
It's basically the same model. Like this means like this. The architecture is the same, and they have the same parameters. And the idea is like you have two sentences at the same time. You plug it into your input. You have the one single loss. Here this is the idea. Like you can backpropagate through this whole thing. But at the end of the day, there's one function for one BERT, another function for the same function for the BERT, because they share the parameters, and you want to update these parameters. That's the whole idea. Okay, cool. Good. So we should talk about we talked about the nitty-gritty details of attention last time, but the intuition wasn't really clear. So what the heck is going on here in these attention layers? Like, why is it important? Why we're doing the dot product of one vector with one word, each word with every other word, what it's actually this attention look like. So people started looking into, there's a reason why it worked and why designers of BERT developed it in a way. But after BERT was introduced with all these very great results, like boost in all these 11 different tasks, people started looking into like, oh, what is attention actually? What is BERT actually learning about language? Because you can kind of inspect it, but it's just too big. So you try to kind of look into by examples. So the team so this is by Chris Manning in Stanford, Omer Levy back then in, I don't know where he was, and Kevin Clark, and the second author, I don't know, Kandelwal. They took the BERT model and look into like what the attentions are actually doing from the linguistic point of view. So what linguistic features does BERT learn? Because the attention, I mean, if you look at the attention, it means which word attends to which other word. So there is some strength of association, and you can inspect that based on the input. So it has a clear meaning, like how much a particular word will be weighted when computing the next representation in the current word. So there is some importance for some words for other words, which will be useful in the next layer. And this is what attention is sign of capturing. So they try to look into that. Excuse me. And so they took the they look into many different things, but one of them was sort of like syntactic capabilities of these attention heads. So they took some data from Wikipedia, like 100 sentences or 1,000 sentences from Wikipedia, and put it through BERT. Like let it just go the forward pass of BERT, and for each layer, and you have 12 layers, and each head you have maybe like 12 heads, attention heads. They're initialized differently, so they will learn something different. So they look into what these layers and attention heads, how the attention looks between every word and every word, at each layer, at each attention head. And they took sort of the weight into like, well, does this attention weight predict something about some linguistic category? So they said like, oh, if I take the attention head, can I use it, just the information, like just the strength of association, is it a strong signal for me to predict whether this is something linguistically important? Like is there something about a part of speech? Is there something about, I don't know, coherence? Is there something about the tense, past tense, present tense? What is there? When they try to use the signal, just the signal from the attention, to predict something meaningful in linguistic view. And they actually find something very cool, that these attention heads, so the strength of association, that it finds objects of verbs. What does it mean? I took the pen. So the pen is the object of I took, and took and pen would have a very strong association in the attention, which makes linguistically sense, because the word, the verb, and the object of the verb are somehow related. I mean, you should take into account the context. So it learns strong association between these two words. Determiners of nouns, VA, objects of prepositions. So I was in the school, so in and school have a strong association because it's like some prepositions for objects, and so on. And this is a strong signal, so they actually use it for, I mean, you could, based just on this strength of signal, you can classify this linguistic category with good accuracy. And what they're concluding is that these results are super intriguing and very interesting because of the behavior. I mean, this is learned just purely from self-supervised training on unlabeled data. So this is interesting. Like the BERT model is able to pick up knowledge of syntax just by training on Wikipedia. Just by, you say like, oh, here's data, do whatever you want. And it's able to learn not in all layers, in all heads, but in some layers and some heads, it's actually picking up something which is linguistically meaningful, like on the syntax level. And here's an example from this paper. I hope it's readable. So this is a layer 8. So there's, I don't know, like 12 layers. So you take the 8th layer and head number 11, whatever. So it's like they look into this. And there's one example. So you take the sentence, this is like the complicated language in the huge view law has muddied the flight. Oh, I have no clue where it's coming from. Wikipedia, whatever. So this is the sentence, and they look in the attention between each word and each word. And the darker the word, so this is the strength of association. Basically, the darker the line between these two words, the stronger the attention between these two words is. And red is connected to red. And here's interesting. So this is showing, for example, that determiners attend to their nouns. So for example, the is strongly attended to language. So the complicated language. So there is a strong association. Or here, law. The huge new law. So or D-flight. I mean, it's not surprising for us that the determiner, the article like D and A, is connected to the noun, even like it's skipping over the adjectives a little bit. I mean, from us, we understand the language, so we know, yeah, of course. I mean, if you have a determiner, then it has to be a noun later on. But BERT is actually learning this automatically just from unlabeled data. It's really paying attention. It knows, oh, if I'm at the, I should pay attention to the noun like down the road. So it's just picking up from unlabeled data. It builds some sort of syntax representation. Or here, the 40-year-old former General Electric co-executive. So this is interesting. Like the word is really far away, but it really has a strong association to the determiner here. So there is a strong attention. So the attention is very high here. So the word attends to the other word for a linguistic reason. And of course, this is just a pickup example. There's lots of noise in there. There's so many attention heads and attention. I mean, this is one example. There's more in the paper if you want to, just look it up and like a 6-page of this paper. And so there's very many attention heads, which makes no sense for us. Like, if you look at a sentence and there's some association between the two words, you would say like, I don't know. But some of them, this is interesting, like not all of them are sort of interpretable, but some of them actually make sense from a linguistic perspective. This is interesting. So the model is picking up something we know about language from the structure of the language, at least English, and it's very strong signal. So it's learning things about language. And it's learning more about also like maybe meaning of words and some pragmatic things. Questions? So there is much more research into interpretability on understanding BERT, but I think it's like more like research oriented. So if you're interested, start with this paper and go to the rabbit hole of Google Scholar and ACL Anthology, and you will find like very nice works in there. But I think it's enough for the lecture. So the BERT thing was a game changer. It stays on shoulder of many clever concepts. I mean, we didn't talk about all these concepts because attention is not new in BERT. Like, attention was kind of brought into NLP in 2015 in regular neural networks for machine translation. And there's different variants of attention, but this one in particular in transformers is like the one attention everybody's using these days. And what do we know about how BERT works? How BERT works, as I said, like you can do some sort of probing, you can do explain predictions, you can do so many things. One example, which is linguistically interesting, is this paper of the group of Chris Manning. And there is actually a very, very nice paper in Transaction of ACL, paper by Anna Rogers and other authors. They entitled BERTology. So there's a BERTology paper, which is kind of a nice overview of BERT. Highly recommended reading if you're interested. It's very, very well written, lots of insights on a high level, highly recommended. Okay, this is it for today's lecture. So, any questions? Not the case. Thank you very much.